Hi, everyone. The past few days, we've been implementing this concept of calorimetry. And calorimetry is a measurement of energy changes in a chemical reaction, or it could be during a physical change or during a nuclear reaction. To carry out calorimetry, we make some assumptions in the lab, and those assumptions can obviously lead to some sources of error. We assume that the vessel that we are using, called a calorimeter, is purely isolated and that no heat is transferred from the system to the surrounding or from the surrounding to the system. We also think about the calorimeter being a perfectly insulated vessel where no heat is absorbed or released from the container itself. And we also make an assumption that when we are using very dilute solutions, which we have not yet done, but very dilute solutions would have a very low concentration. So something like 0.1 moles per liter of hydrochloric acid. We assume because most of that solution would be made up of water, that it will also have the same specific heat capacity as that of water. We have used the specific heat capacity lab with the metal calorimeter. We could have also have used 2 styrofoam cups as a simple calorimeter. When we did the burning of the Cheeto lab in class, we used a pop can with another can over top as a pretend bomb calorimeter. We've seen in a previous video that what would happen is a food source would go here and we would ignite that food source and we'd be able to track the reaction and the change in temperature of the surrounding water. Today we're going to get introduced to a new formula called delta H, and I'll talk about that shortly. But I do want to make a couple of changes to this worksheet that you have. It says if Q of the surroundings is positive, then the change is exothermic. That is not a true statement. This should say if Q of the surroundings is negative, so make that change, please, then we consider the reaction to be exothermic. And we've learned that exothermic means that there is a release of heat energy from the system to the surroundings where the temperature would be going up. In this case, your Q would be a negative value, and something else that we're going to learn about today, your delta H will also be negative. If the surroundings is positive, so meaning the heat calculation results in a positive value, then we say that the change is endothermic. And your delta H value will also be endothermic. Now, what does that delta H mean? So we've learned previously, so let's take a look at the back of the sheet, okay, that we implement Q equals MC delta T formula to calculate heat. M being mass, C being specific heat capacity, delta T being change in temperature, final minus initial. We can also employ a new formula, delta H, which is known as molar enthalpy. We know that Q equals heat, and we've seen this variable N before. We need to remember that N represents moles. So if I was to come up with a definition, enthalpy is really how much heat, the amount of heat gained or lost per mole of a substance. So let's write that down. Amount of heat gained or lost per mole of a substance. So we're going to have to use this above formula to get us the numerator, but we have to recall from grade 11, what are some ways in which we have to figure out mole value, because they might not just give us the mole value of the substance. So up above here, if we can maybe use this blank space to recall some ways that we can calculate moles. The first way is by taking the mass of a substance, if it's given in the question, and we divide it by the molar mass. So you may want to recall that molar mass we get from the periodic table. So when I take a look at my periodic table and I use the average atomic mass that is reported for each substance, if I was to take a look at carbon, for instance, 12.01 grams of carbon, if I was to weigh that out on a scale, is equal to 1 mole of carbon. Now, I would never want to count out how many atoms of carbon that would be equal to because I wouldn't be able to do it in this lifetime. Remember that 1 mole of anything is equal to 6.022 times 10 to the 23. So that is referred to as Avogadro's number. The quick way of getting to that mole value is to look at its molar mass, or the average atomic mass, we call it. The other way is if in the question they give you number of molecules or number of atoms, we can calculate moles by using this symbol, which represents number of molecules, number of atoms, all over Avogadro's number. So this represents number of molecules, if it's a molecule, or if they're talking about number of atoms. And then when you divide by Avogadro's number, you'd want to put that into brackets. That is 6.022 times 10 to the 23, and that would be atoms or molecules per mole of a substance. Okay, so that's how many you have. The last way to calculate moles is if they give you concentration. Moles is equal to concentration, also known as molarity. Now that means that this has to be in moles per liter, okay, times volume, which is in liters. So you're going to notice that liters cancel out and you're left with moles. So this could also be a capital M for molarity. These are the 3 different ways that you may need to use in order to get your denominator in the enthalpy calculation. Let's take a look at the first question. In this first question, they tell you that you have 5.2 grams of sodium hydroxide, and that undergoes a reaction that results in a temperature of water, 250 milliliters of water, and the water temperature increases from 21 degrees Celsius to 28 degrees Celsius. Calculate heat of the reaction in kilojoules per mole. Now, heat, when I hear the word heat, I think of Q. But because they said per mole, that means I'm really looking for delta H. So delta H of the reaction, and I use Rx, that just is short form for reaction. That is my unknown variable. So up above, when we're referring to delta H of the reaction, that means I look at the substance that we're dealing with and it's sodium hydroxide. My target equation is going to be Q of sodium hydroxide. Now, if you don't know the formula for sodium hydroxide, you can certainly look that up. All over moles of sodium hydroxide. When I know the formula for Q, I look that up here, MC delta T. Do I have all of that information? Do I have mass of sodium hydroxide? Yep. Do I have specific heat capacity? No, they did not give that to me. Do I have delta T for sodium hydroxide? Initial temperature? Do I have the final temperature? Nope, I only have the final temperature. I don't have initial. So what am I going to do? I have to remember that Q lost equals Q gained. Okay, so if I can figure out Q of the water, then I'll know Q of the sodium hydroxide, and all I would do is flip the sign. So let's go ahead and do that over here. I have enough information to calculate Q of the water. I know the mass of the water is 250 milliliters. I can equate that to 250 grams. Specific heat capacity for water, I have memorized. Final minus initial. So 28 degrees, final minus initial, ends up with 7 degrees Celsius. So what I'm going to do is I'm going to calculate that value, and I'm going to see what I get on my calculator. I punch that in, I get 7,315 joules. Grams cancel out, degrees Celsius cancel out. This is joules of my water. So that means that Q of my sodium hydroxide is the negative value of that. So when sodium hydroxide reacts with water, it is losing heat energy to the water. The water is gaining the heat energy. Because I have flipped the sign there, that's how I know which one's losing, which one's gaining. If the water ended up being a negative value, then the sodium hydroxide would be a positive value. Okay, so Q lost equals Q gained. Now, what I can do up here is I can change this formula up here if I want. If I'm looking to try and do this as one rearranging of formulas, I know that if I take the negative of Q of water, okay, that's what I've done, all over. Now, what is the formula for moles of sodium hydroxide? Because they give you mass, you can take mass of sodium hydroxide all divided by the molar mass of sodium hydroxide. Okay, so this is what the formula would look like if I was trying to show this as one formula. Okay, if not, you can certainly break it down into various steps. Okay, so at this point in time, this is what I have entered on my calculator. Okay, so I have this value already up on the top. On the bottom, the mass of sodium hydroxide, is 5.2 grams. There we go. And the molar mass I looked up. Now, what you would do on your periodic table is you would say, okay, 1 sodium, 22.99, plus 1 oxygen is 16, plus 1 hydrogen, 1.008. You add those together, and that would give you your total molar mass of sodium hydroxide. I got a little lazy and I just looked it up on the internet. You can do the same as well, but if you need more practice, then you can certainly do that. So 39.997 grams per mole. Okay, now, and I'm going to enter this on my calculator. Oops, I shouldn't have cleared that out. Okay, there we go. I'm going to divide this. Now I'm going to use my bracket keys. Divided by 5.2 divided by 39.997, close bracket. That tells me what the bottom value would be. And I'm going to push equals again. And this is the number that I get. Now, this is a really big number. What would my units be right now? Well, my units, let's write this down, negative 56,265.01058. That would be joules per mole. The question is asking us to report our answer in kilojoules per mole. What you need to know is that there are 1,000 joules is equal to 1 kilojoule. You're going to divide this by 1,000. And that just means that you are going to move your decimal place 3 spots to the left. 1, 2, 3. The next thing that I need to consider when I'm reporting my final answer is how many significant digits can I report to? The mass is 2 sig fig. Volume of water is 2 significant digits. Because of that 0, there is no decimal there, so that is not significant. Temperature, 3 sig fig. So I can only be accurate to 2 significant digits. So my final answer in this case is negative 56 kilojoules per mole. And what I'll do is I'll maybe highlight my final answer just so that stands out. Okay, so what this tells me, because I have a negative enthalpy calculation here, that tells me that this reaction is exothermic. Exothermic meaning that the surrounding temperature went up and that this reaction got very hot. And so energy is flowing from system to surroundings when sodium hydroxide reacts with water. Let's take a look at the question below. In this reaction below, we see that we have ammonium nitrate as a solid becoming ammonium nitrate aqueous. So this just means that this is a dissolving process. So this is not a reaction. Dissolving is a physical change. So notice instead of using Rx here, we just say delta H of solution. They want to know what would be the final temperature in a calorimeter containing 250 milliliters of water at 22.4 degrees Celsius if you put 10 grams of ammonium nitrate in that water and it's dissolving. Salts will cause solutions to get hotter or colder, right? So some salts don't really have any effect, but other salts, like if you see in a chemical cold pack, they will make that solution become very cold. And this is the main salt found in chemical cold packs. So we want to know, what effect will this have? We have 250 milliliters of water. This is the initial temperature. They want us to figure out what the final temperature would be. The only way that I can figure out final temperature is I know the mass of the water, specific heat capacity of the water, and delta T. I know that my delta T is final minus initial. So in order for me to solve for this, I would have to rearrange my delta T. In order to figure out delta T, you would have to take Q of the water divided by mass of your water all over specific heat capacity of your water. I do not have Q of the water. I do have the mass of the water and I do have specific heat capacity. So in this scenario, I have two unknown variables. I don't know the final temperature, which is part of delta T, and I don't know Q. So I have to figure out a way, how do I get Q of the water? Well, I have to take a look at, I'm given delta H of the solution. This applies to this particular salt or compound. I'm also given the mass of that compound. I do know that delta H of ammonium nitrate, okay, so that's the solution, that's what I'm looking for, would be equal to Q all over N. And this N would be for ammonium nitrate, and this Q would be for ammonium nitrate. I can rearrange this formula because I'm given delta H. I can rearrange this to solve for Q. So let's go ahead and do that. If I want to solve for Q of ammonium nitrate, I want to take delta H multiplied by moles. And again, delta H of the solution for ammonium nitrate times moles. I don't have the mole value per se, but I do know the mass. What you can do is you take mass of your ammonium nitrate and you divide it by the molar mass of ammonium nitrate. So let's go ahead and do that. Delta H is 26.2 kilojoules per mole. The mass that's given is 10.0 grams. And again, I looked up the molar mass for ammonium nitrate, and it is 80.052 grams per mole. Let's plug that into our calculator and see what we end up getting. 26.2 times, close bracket, 10 divided by 80.052, close bracket, and I get a value of 3.272872633. Now, what are my units here? Well, let's take a look. Grams cancel out, moles cancel out. My units are kilojoules. Okay, this is great. If I know Q of ammonium nitrate, I know Q of my water. What must I do to this value to make it Q of the water? Well, we know that Q lost equals Q gained. So in this case, ammonium nitrate, Q gained. So that means Q of your water, and I'm going to be a little bit lazy here, I just flip the sign. Okay? So what this is telling you is the ammonium nitrate is having to gain energy from the water in order to get it to dissolve. Okay, so the water is losing heat energy to the salt to help it dissolve. So we have this value. Now this value is in kilojoules right now. We must convert it into joules because in this calculation, I'm going to be using the specific heat capacity of water as 4.18 joules per gram degree Celsius. In order to have like units to cancel out, I must convert this into joules. Okay, so I'm going to put a negative in front. That becomes my water value in kilojoules. I'm going to multiply by 1,000. So in order to go from kilojoules to joules, you multiply by 1,000. And in order to go from joules to kilojoules, you divide by 1,000. So I have enough information now that I can plug in. So I have negative 3,272. Notice I am not doing any rounding in the middle of my equation. You cannot. Only at the very end do you determine your number of sig fig. The mass of my water is 250 grams because 250 milliliters equals 250 grams. The specific heat capacity is 4.18 joules per gram degrees Celsius. You can see here, joules cancel out, grams cancel out, and your delta T is going to be in degrees Celsius. So I still have this in my calculator, so sometimes you don't even need to clear it out. I'm going to divide it by, put these in brackets, divided by, close bracket, 250 times 4.18, close bracket, there we go, push equals, and my delta T ends up being negative 3.13193553 degrees Celsius. We're not done. So this question is asking us to solve for TF. So what I do know is delta T equals final minus initial. If I rearrange this, because I have delta T now, if I want to get TF by itself, I bring TI to the other side of the equal sign. So TF is going to equal delta T plus initial temperature. So this is my value. I haven't rounded or anything. What was the initial temperature of the water? Well, let's go back up here. It was 22.4. So I'm going to take that, and this says add it to 22.4, and you get 19.26806,447 degrees Celsius. That would be your final temperature. What am I going to report my answer to? Well, you can only report your answer based on what's been given. Because of this measurement of water is only 2 sig fig, everything else in the question is 3 sig fig, you can only be accurate to 19 degrees. So I did sort of run out of room here, but I would like you to make sure that you write out this value plus your TI. You do need to show your work. So whatever you do in your calculator needs to end up on your paper in order to show good formatting of your solutions. If you don't do that, you are not going to get full marks. So if you just went from like this to this step, I have to see the thought process that goes along with it. Okay, so 19 degrees Celsius. I am not going to require you to do therefore statements. However, box your final answer just to help me out a little bit, and then I will see. How do I know that this was an endothermic process? Couple of things that point to that evidence. Your temperature dropped. If your temperature drops, then that means it is an endothermic process. Also, the fact that the delta H given was a positive value. So what I'm going to ask you to do is to do some more of these practice calculations in a thermodynamic assignment. That is going to come after you learn a little bit more about bonds breaking, bonds making, and the energy associated with those in your endothermic lesson that is coming after this one here. Okay, so it will sort of all come together in calculating enthalpy and how to recognize and illustrate endothermic and exothermic reactions in various ways. In the assignment, you're going to have to use this formula as well as some of the previous ones that we have learned about negative MC delta T equals positive MC delta T when you're trying to find final temperature, or you may have to look up how to do molar heat capacity. So please use your notes to aid in that assignment.